Designing an inverse filter for an original maximum phase filter is always going to involve approximation. In this case, we're going to try to do that approximation by means of an FIR compensator. So here's the model we've got. We've got a signal that's being generated. It's going to be some sort of triangle plus some high frequency content coming in. It's going to hit a maximum phase filter. This is our initial filter that we've got. It is maximum phase. Its coefficients are B equal 1, minus 2, and 3. It's easy to confirm that that's a map. We're going to look at the original on the yellow trace of this signal analyzer 1, and we're also going to see what happens when that pulse passes out through that initial distorting filter. Once we've done that and examined that for a moment, we're going to carry out a design procedure here in Sketch-a-Filt. It's going to be implemented in this block right here, so that this will serve as the inverse filter, and we'll pipe that on out here to see on the white trace of the second analyzer hopefully an improved situation. We'll be able again to compare that with the original, albeit with some delay. And furthermore, at the end of the situation, we'll be also able to look at the restoration error right here on the single trace analyzer out here, and furthermore have a look at the overall transfer function, impulse response, and so forth. So let's run it. We want to look primarily on this scope right now to start with. There are two things overlaid here. Let me get rid of the white one. This is our original signal on the yellow trace coming right through here. It's got a bit of low frequency, a bit of high frequency content. When I restore the white one, you see that what's happened is mainly the high frequency content has been hiked up here, and in fact that shows up as a much more grassy sort of look right here. We'd like to get that grass level back down to the original level that we had, and we're going to give that task to an inverse filter. Let me stop the model and have a look here at first how I can get my filter into Sketch-a-Filt. I'll do that by putting it into the workspace. I'll actually type B equals 1, minus 2, minus 2 and 3, so that it's in the workspace, so that when I come over here, click on this block and bring Sketch-a-Filt to life, there's some sort of background situation which is there, and I'm going to now import the filter that I just designed. Import guest filter from workspace. There's only one there, and it's B, so I'll bring it in, and it's telling me that I've got a longer display than I actually need for 3 coefficients. I'm not much worried about that. In fact, I'm going to get rid of the old profile that was up there, and I see that here's my gain and the roll-up situation which is causing my high frequencies to be accentuated. I'm going to change this guest filter into a target profile. I can do this in Sketch-a-Filt by promote filter's magnitude to target profile and let the guest be the one that receives that effect. And here it is. The red, this is now turned into a red thing, and I'm going to be exporting that to the target profile calculator. So I go up to the menu item up here at the top, and I can see that what I've got is this the full complex transfer function which we've just been talking about. Now if this is what's causing the trouble, I want 1 over that to be the antidote. So I go down to this button right here and go to 1 over what I see on display A, and then I'm going to store that result on display B, and here it is. But this is no good to me in the profile calculator. I've got to ship this back to Sketch-a-Filt so I can do a design job. So I come down here, send profile to Sketch-a-Filt. Which one? The one which is on B, and come on, and it's gone. Okay, and here then is the new red thing, my new profile. I'm going to get rid of the previous one. Don't need to look at that anymore, so I can see how well my approximation is. I've got a frequency sampling approximation coming on here by default. It's way high. I don't want it to be that high. I'm going to come down here to about 11 and see how well that fits. It fits pretty well. You can see that it's not going to quite be a perfect inverse filter, so I'm going to try to go a little bit higher, maybe 13. Ah, that's locked on quite nicely. I'm going to take that one with 13 coefficients and allow that to act as my inverse filter. You can see it here. It's on the icon. It's been taken there now. And so now when I start the model, I should be going through the original distorting filter and hopefully through a satisfactory de-distorting filter or inverse filter. Let's just see what happens. I'm going to be looking at the result of this on, I'll look at it first on D2. Yes, I can see that apart from some delay situation, they're looking pretty close. I'd like to know what the delay should be. I'll just try checking it out here manually, visually. I'm getting up to 6. 7 seems to be pretty good. I can fine-tune this by looking at my signal analyzer single trace here and look at the restoration error, and I bring this up. That's still pretty high right there. I don't think I've got it lined up as well as it could be, so let me call that back up and see if 6 is not so good. Let me look at 7. I'll type that. Bang. I've got the best I can do right here. I've got a 0.05 error, and that means that I've got these things lined up as best I can. And here then is the situation. If I get rid of the white one and the yellow one, you can see there's not very much difference, but of course we know there is some difference, and we haven't obtained a perfect filter. It's a question then of what have we obtained overall, and we can look at that by piping out the B's and the A's of the original filter and also the inverse filter or the approximate inverse filter, and have a look at the whole business on the CPIG analyzer. You notice that my impulse response looks very good, because it should overall be an impulse at 7, because 7 was the amount of delay I had to put in here. That's not too surprising. The gain is quite flat. I suppose I could go up to maybe 15 or higher for my coefficients, and this would get even flatter. What about the group delay? Group delay, not too bad, and again it's about 7 samples. So I've obtained a quite serviceable inverse filter here simply by means of FIR design.